Hi, everybody. All right, so today we're going to do a quick lesson on polarity. So we're going to be talking about polar bonds and polar molecules. So it's not the same thing. Polar means the same thing, but there's a difference between a polar bond and a polar molecule. And just because a molecule contains polar bonds doesn't mean the molecule is going to be polar. Right? So yes, a molecule has to have polar bonds in order to be polar, but just because a molecule has polar bonds doesn't mean it has to be polar. So we're going to talk about what polarity means and how to tell if a bond's polar, and then also how to tell if a molecule's polar. All right. So let's go to it. Now, before you kind of watch the full video here, you should look over the polarity PowerPoint with the polarity guided notes. Or you should kind of just skim through that so you're kind of familiar with everything that's going on. But essentially what I'm going to talk about in this video essentially goes through these guided notes, maybe not in the same order, and kind of goes through this PowerPoint. Okay, so again, we want to talk about polarity of bonds versus polarity of molecules. All right, so first let's just make sure we review and understand what a covalent bond is. And when we say polar bond, we really mean polar covalent. And if we say non-polar bond, it's non-polar covalent. We're not talking about ionic bonds. We're talking about, if we say a bond's polar, it's a covalent bond, but it's polar. So we got to understand what that means. All right, so a covalent bond is when electrons are being shared. So you can write it like this, or you can write it like this, but this is 2 electrons being shared between the hydrogens. Here we have a triple bond, a triple covalent bond. We have 6 electrons being shared between the carbon and the oxygen. Here we got another single covalent bond, 2 electrons being shared between the fluorine and the hydrogen. So let's just look at these bonds and identify them as polar or non-polar, and then maybe we'll lead to it. Okay, so this is a non-polar covalent bond. This is 100% covalent, okay? 100% non-polar covalent bond. This is a polar covalent bond, and this is a polar covalent bond. So what's the difference? Well, if you kind of looked at there, you notice that this bond is between 2 of the same element, but these bonds that are classified as polar are bonds sharing electrons, covalent bonds, between 2 different elements. Okay, and so really that is the key to polarity. Okay, so we got to understand what it means, but that's the key to polarity. If you have 2 things that are the same thing, like 2 H's sharing electrons, that's going to be 100% non-polar. Okay, when you have 2 different things sharing electrons, normally that's going to be polar. Okay, and pretty much anytime you have 2 different elements sharing electrons, you're going to have some polarity, but we're going to give it a range. We're going to say it's non-polar, or we're going to say it is polar. So let's talk about what I mean by that. Okay. So a polar bond, again, is short for polar covalent bond. And what it really means is the electrons are being shared, but they're unequally shared. So if you're polar, you're sharing electrons, but you're not sharing them equally. Okay, an unequal sharing of electrons. So like in this bond, these electrons are being shared 100% equally, because there's no difference between what's on this side and what's on that side. Equal sharing. Okay, this is a non-polar bond. Okay, but here, these electrons are not going to be shared equally. They're being shared, but not equally. Okay, so this is going to be a polar bond. So what causes the unequal sharing of electrons? It's due to the electronegativity difference between the atoms in the bond. All right, so let's talk about this bond in particular. We got to remember our electronegativity trend. If you remember our electronegativity trend, fluorine is the most electronegative element. And I'm in the PowerPoint, we kind of have this periodic table to remind you. Notice, like, here are all the electronegativity values. Notice we don't need to include the noble gases. But, notice fluorine is 4, okay? Hydrogen's 2.1, okay? So there's a big difference in electronegativity there, right? What is a 1.9 difference in electronegativity. Now, what electronegativity is the ability to attract the electrons that are in this bond to that element. So fluorine has a greater electronegativity. That means those electrons in the bond are going to get pulled closer to the fluorine atom and further away from the hydrogen atom. Now, understand what that does. As the electrons get pulled over this way, this side of the bond becomes negatively charged, right? Because electrons are negatively charged. So if electrons are hanging out over on this side more than they are on this side is going to become negatively charged, and that means this side is going to become positively charged. And that's what polarity is, when you have oppositely charged sides to a thing. So what makes a bond polar? When the bond has oppositely charged sides. So in this bond, this side of the bond's negative, this side of the bond's positive. That's a polar bond. This is a nonpolar bond because they're equally sharing electrons. So there is no negative side and there is no positive side, so it's nonpolar. But here, we're not sharing the electrons evenly, and it's because fluorine's better at attracting those electrons than hydrogen is, so they spend more time around the fluorine atom than they do around the hydrogen atom, and that creates the polarity. Okay? So whenever you have an electronegativity difference between the atoms that are sharing electrons, you're going to have polarity in the bond, okay? And again, all polar means is oppositely charged sides. Okay, so let's look at these bonds. All of these bonds are polar. There is an electronegativity difference between these. And again, you don't have to memorize your electronegativity values. Okay, you can always look up a chart. Okay, so where am I getting these differences? Okay, so this the difference between nitrogen and carbon would be 3 minus 2.5. Between oxygen and carbon would be 3.5 minus 2.5. And the fluorine in carbon would be 4.0 minus 2.5, right? That's how we're getting those differences, all right? So this bond is polar, but it's not as polar as this bond. The bigger the difference in electronegativity, the more polar the bond, okay? So this has an electronegativity difference of 0.5, this has an electronegativity difference of 1.0, and this has an electronegativity difference of 1.5. Again, so all these bonds are considered polar, but if you wanted to know which one was more polar, you're looking for the most electronegativity difference between the atoms. And you can look that up, okay? Just look up electronegativity values and this chart will pop up. Another thing we want to take a look at is this chart here. So I'm just going to make it bigger so we can see it. Okay, so this this chart's going through characteristics of bonds. So let's think about it this way. When you have electrons being shared, but they're not equally being shared because of the electronegativity difference, eventually you get to a big enough electronegativity difference that instead of being a covalent bond where you're sharing electrons, you get a complete transfer of electrons, and that's when you get ionic compounds, all right? Now this range is kind of a range where, if we want to be technical, we call, if the difference in electronegativity is 0.4 or less, then we're just going to call it covalent, okay? If you're 0.4 or higher, we're going to call you polar, but the higher you are, and just because you're 1.8 doesn't mean you're ionic, right? This bond here has a 1.9 difference, but it's still considered a covalent bond. It's polar, it's very polar. But the bigger the difference in electronegativity, the more polar the bond. Okay, so this is a difference of 0.5. So remember, 0.4 is kind of our cutoff. So 0.4, less than 0.4 is nonpolar, more than 0.4 is polar in terms of electronegativity difference. Okay. But when in doubt, because like if you don't have your electronegativity values memorized, which you don't need to do, when in doubt, if it's a bond between two different elements, just assume that it's polar, unless you're kind of told otherwise, or unless you have your values. If you actually have your values available to you, then you could use this chart to determine whether or not a bond is polar or non-polar, okay? But when in doubt, the only one that I would remind you that is not polar is carbon bonded to hydrogen. You need to memorize that carbon bonded to hydrogen is a non-polar bond, okay? So again, what does polar mean? You have oppositely charged sides to the bond. So this little symbol right here just means partial. So this side of the bond has a partial negative charge, and this side of the bond has a partial positive, okay? Now, how do you look at a polar bond and know which side's negative and which side's positive? the more electronegative element gets the negative charge, and the less electronegative element gets the positive charge. So looking at this bond, I know that this side's negative and this side's positive because fluorine's more electronegative than hydrogen. Okay, so this is one way to show the opposite charge sides to the bond. And another way to show it is you draw a positive sign above the positive side of the bond, and then you extend the positive sign with an arrow towards the negative side. Okay, so what we're trying to say here is if you think of a big electron cloud surrounding the molecule, kind of the charge of the cloud is more negative on this side and more positive on that side, kind of. It goes from positive to negative, okay? So again, the more electronegative element gets the partial negative charge, and the less electronegative element gets the partial positive charge, okay? So here we got the same thing, okay? Here is hydrogen and chlorine. We know chlorine's more electronegative than hydrogen based on the electronegativity trend. And so this is going to get my partial negative, and this is going to give me my partial positive, okay? Another kind of vocab word to know is a dipole, okay? So in order to be polar, you have to have opposite dipoles. So the dipoles are the different charges to the different sides. So here is a negative dipole, and here's a positive dipole. So how do I know this bond is polar? Because it has oppositely charged dipoles. It has a negative dipole and a positive dipole. And when you have oppositely charged dipoles, whatever you're looking at is considered to be polar. So this bond is polar because it has oppositely charged dipoles. And we know that based on electronegativity, okay? So in order to be a polar bond, you have to have opposite dipoles, all right? So here's the CF bond. Here's the negative side of the bond, the positive side. You don't have to use the partial notation, but it's good to understand that it's not a full positive charge and a full negative one charge and a full positive one charge, because we didn't completely transfer the electrons. We're just unequally sharing the electrons. That's why technically it's partial negative, partial positive. But we really need to know where the dipoles are and which dipole is which. So in this bond, this is going to be the negative dipole because fluorine's more electronegative. This is going to be the positive dipole. And then these are just kind of different ways to kind of notate the same thing. All right. This shows what we call the dipole moment of the molecule. It's positive over here and negative over here. And as we go from this side of the molecule to this, it goes from more positive to more negative, okay? But here are your dipoles. Here's the positive dipole, here's the negative dipole. Okay, so that's polar bonds, all right? But what about polar molecules? Well, again, to be polar, the thing that you're classifying as polar has to have opposite dipoles, oppositely charged dipoles. So to be a polar bond, one side of your bond has to have a positive dipole, the other side of the bond has to have a negative dipole. Well, the same thing's true about a polar molecule. For a polar molecule, one side of the molecule has to have a positive dipole, and the other side of the molecule has to have a negative dipole. You have to have oppositely charged dipoles in the molecule, okay? So let's look at CO2. A lot of times we like to use CO2 as an example of a non-polar thing, because it's easy to see why it's non-polar, even though it has two polar bonds. So if we look at our CO2 molecule, that bond between carbon and oxygen is polar. There's a big difference in electronegativity there and there. So we got a polar bond over here, we have a polar bond over here. But if we highlight our dipoles, right, the carbon's in the middle with a positive dipole, and each oxygen would have a negative dipole, okay, notice that when we cut our molecule in half, we don't have opposite dipoles. We have a negative dipole on this side of the molecule, we have a negative dipole on that side of the molecule. We don't have oppositely charged dipoles, so therefore the molecule is non-polar, even though it has polar bonds, okay? But now if we look at H2O, we know, coming in from biology, we know that water's polar, but this is why. If we look at water's dot structure, right, it's bent-shaped, okay? It's not symmetrical, it's asymmetrical. And if we assign our dipoles and we cut the molecule in half, notice that we have a negative dipole on this side and we have positive dipoles on that side. So we do have oppositely charged dipoles to the molecule. So this molecule is polar. It has a negative dipole and it has a positive dipole. This molecule is nonpolar because it has two negative dipoles. It doesn't have an oppositely charged dipole on the other side of the molecule. But this does. Negative dipole, and over here, positive dipole. All right? So here's how we technically determine. If you're asked about a bond being polar, it's just, well, if it's two different elements, it's probably polar because there's a difference in electronegativity. And if it's two of the same element, it's nonpolar because there is no difference in electronegativity. We want to remember that C bonded to H is also nonpolar, but that's basically it to figure out if the bond's polar or not. But to figure out if a molecule is polar or not, we got to know if the molecule is symmetrical or asymmetrical. If it's a symmetrical molecule, we know it's nonpolar. Okay? If the molecule is asymmetrical, it's going to end up being polar. All right? So here I have, we have a molecule with 4 very polar bonds. Okay? But the molecule itself is nonpolar because this is a symmetrical molecule. All right? All right. So how do you know if you're asymmetrical or not? Because it's hard to tell based on dot structure, because dot structures really aren't good representation of three-dimensional images. So it's kind of hard to tell. So you kind of follow these rules. Okay? If you have a lone pair on your central atom, you're probably going to be asymmetrical. You're going to be polar. The other thing you could have, and you could have both or just one of these, and if you have one of these, it's going to end up being polar. If you have different things bonded to the central atom. So the reason why I know this is a symmetrical molecule is I don't have any lone pairs or unshared pairs on the central atom. But also, all the things coming off of the central atom are the same thing, fluorines. I have 4 fluorines. If I had changed one of these fluorines, or maybe a couple of the fluorines to a different element, then that would be asymmetrical and it would be a polar molecule. But because these are all the same, and there is no lone pair on the central atom, that's nonpolar, okay? So I know that's nonpolar, but if I look at this one, I would know this is polar because it's asymmetrical because I don't have the same things coming off the central atom. So it can't be symmetrical, right? Okay. I look at BF3, those are 3 very polar bonds, but the molecule ends up being nonpolar because it ends up being symmetrical. It's trigonoplanar, it's a symmetrical shape, but the reason why it's symmetrical is because no lone pair on the central atom, and these things coming off the central atom are the same, so symmetrical, nonpolar. But this is not a very polar bond. Nitrogen's high in electronegativity, so is fluorine. Fluorine's more electronegative. But there is a difference, so that's a polar bond, polar bond, polar bond. So I do have polar bonds, and because I have a lone pair, that makes this molecule asymmetrical, so that is going to be a polar molecule. It's an asymmetrical molecule, trigonopyramidal, okay? So here's trigonoplanar that's nonpolar because I don't have any lone pair on the central atom and these things are the same, oxygen, oxygen, oxygen. But here's trigonoplanar that would be polar because I have different things coming off of the central atom. So this is going to be an asymmetrical molecule, it's going to be polar, okay? So that's polarity. That's what polarity means. You have oppositely charged dipoles. And if you do have oppositely charged dipoles, you're polar. Okay, so a bond that has oppositely charged dipoles is a polar bond. A molecule that has oppositely charged dipoles is a polar molecule. But just because you have polar bonds does not mean you have a polar molecule. For molecular polarity, you have to look to see if the molecule is asymmetrical or symmetrical. Remember, asymmetrical equals polar molecule. Symmetrical equals non-polar molecule, okay? And if you look at the PowerPoint and the guided notes, like at the very end, you kind of have this slide where it shows you the symmetrical shapes. Assuming that all these things coming off of the central atom are the same, then these shapes are symmetrical. And then you have your asymmetrical shapes, because these are the shapes that have a lone pair on the central atom, okay? So if your molecule is one of these shapes, polar, assuming you have polar bonds, and if your molecule is one of these shapes, nonpolar, assuming these things are the same. If one or more of these things are different coming off of the middle atom, then these would also be polar molecules. All right. So that's polarity, and just take some practice. So go work on your 4-7 assessment, or for polarity, or your concept builders for bond polarity or molecular polarity, and yeah, get to it.